We are in section 10.2, Calculus with Parametric Curves. In the previous section, we learned how to represent curves by parametric equations. We can then solve problems involving tangents, areas, arc length, and surface area with parametric equations. This is a great section because it does go back over a lot of the main topics that we talked about already in Calc 2, but now instead of using a Cartesian equation, we're going to be using a parametric equation. So the first box on here says tangents. It says suppose f and g are differentiable functions and we want to find a tangent line at a point on the curve where y is also a differentiable function of x. Then the chain rule gives dy dt is equal to dy dx times dx dt. And so we know that if the derivative dx dt does not equal 0, we can solve for dy dx, and that's written out there. And it says if dy dt equals 0, then the curve has a horizontal tangent, provided that dx dt does not equal 0. And if dx dt equals 0, then the curve has a vertical tangent. So again, we would have dy dt is equal to 0. We're going to have a horizontal tangent. And dx dt equal to 0. We're going to have a vertical tangent. And then on the next page, it does say concavity, which if we remember was our second derivative. We talked about that back in Calculus 1. And so concavity, it says if the second derivative of f is greater than 0, then it's concave up. And if the second derivative of x is less than 0, then it's concave down. So the formula for us, d squared y over dx squared, and then again taking that second derivative is written there. The example right below says find the equation of a tangent line to the curve at the point corresponding to the value of the given parameter. And it says x equals the square root of t, y equals t squared minus 2t, and then t is equal to 4. And so this is asking for the equation of a tangent line. So that's what we're going to be writing out for our solution. And so for this, we know that x is equal to square root of t, and t is equal to 4. So x would be equal to the square root of 4 or 2. And likewise, our y value would be equal to t squared minus 2t. And evaluating this when t is 4, we have 4 squared minus 2 times 4, which we get as 16 minus 8 or 8. So from these two values that we get for x and y, we know that we have an ordered pair at 2, 8. And then so in order to find the slope, we need to find dy dx, which is going to be, since y is in terms of t, we would be finding dy dt and dx dt since x is in terms of t. And so dy dt is just going to be 2t minus 2. dx dt would be the derivative of the square root of t, which is going to be 1 over 2 times the square root of t. Simplifying this, we get 2 times the square root of t times 2t minus 2. And again, the value of t for us is at 4, so we're going to go ahead and substitute in 4. Doing that, we get 2 times the square root of 4 times 2 times 4 minus 2, which, working this out, we get a value of 24. So that value of 24 would be our slope, which was dy dx. And that's the slope of the tangent line. And again, that tangent line is when t is equal to 4 or when x is 2 and y is 8. And so in order to find the equation of our tangent line, I'm going to put this into point slope form. And so we have y minus y1 is equal to 8. The slope is 24 times x minus 2. We have y minus 8 equals 24x minus 48. And then simplifying this from here by adding 8 to get that y isolated, we have y equals 24x minus 40. And so this again is the equation of the tangent line to our curve when t is equal to 4. The example right below says find dy dx and d squared y dx squared, so the second derivative, for which values of t is the curve concave upwards, and we're given x is equal to t squared plus 1 and y is equal to e to the t minus 1. So in order to find our first derivative, dy dx, we need to find dy dt and dx dt. So dy dt would just be e to the t over, and then dx dt is going to be 2t. And then taking our second derivative, so we have our second derivative. So this would be taking the derivative a second time with respect to x of our first derivative, which is dy dx. And so rewriting this, formula is right up above. We have d dt of dy dx. So taking the derivative again of what we have up above with respect to t over dx dt. And you can see here that this, if these dt's were on, that would be equivalent to the equation that we have to the left. And so going ahead and taking the derivative of what we have up above of dy dx with respect to t, we're going to have to use the quotient rule. And so we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And then dx dt is just 2t. We calculated that up above, and you can always look at the x variable again and take the derivative of that with respect to t. So simplifying this, if you think of this being a compound fraction, and you can multiply by the reciprocal of the denominator, allows us to kind of rewrite this a little bit nicer. And so this is going to be 2t e to the t minus 2e to the t over, and so this time we're going to have 2t squared, which is 4t squared, times another 2t. So that works out to be 8t to the third. From here, we can definitely factor out a 2 in the numerator. And you can also factor out a e of t if you would like. I'm just going to factor out the 2 since that's what I'm going to simplify. And so this would reduce. And so we have t e to the t minus e to the t all over 4t cubed. And since we're looking for where this is concave up, that would be where the second derivative is greater than 0. And again, that was taught in Calc 1. So the second derivative is greater than 0. So since we have our second derivative here, I need to figure out where it's greater than 0. So in order to do this, if you remember from Calc 1, we found our inflection points. And so inflection points would be either where it is, our second derivative is undefined, or where it is equal to 0. So I'm going to put an IP for inflection points. And so this is undefined when the denominator is 0, so when t is equal to 0. And then in order to find those inflection points, we also need to figure out where that numerator, which is t e to the t minus e to the t, is equal to 0. So factor out an e to the t. And we have where e to the t would equal 0, and where t minus 1 is equal to 0. So this would solve to t equals 1. And we know that e of t does not ever equal 0. If you think about what that graph looks like, it never would touch the x-axis, and therefore it would never actually equal 0. So we have two values of t where we have possible inflection points, and that would be at 0 and at 1. And so to figure out where this is, and again, greater than 0, because we're looking only for concave up, I'm going to do a number line and write out a sign chart. And so putting on those possible inflection points where it could change concavity, I need to now substitute this in. So our second derivative, I'm going to select a value that's less than 0, so I'll say negative 1. Select something in between 0 and 1, I'm going to say 0.5. And then select something larger than 1, so I'll say 2. Again, it doesn't matter those values as long as they're in that interval. And so substituting in -1 into your second derivative, you can see that that would be positive. Substituting in 0.5 into your second derivative and that equation for the second derivative, I will box right up above. And when substituting that in, we get a negative, so it's concave down there. And then that last interval, it does change to concave up. So the curve is concave up when, and so it's concave up on the interval from -infinity to 0 and from 1 to infinity. So when t is in the intervals from -infinity to 0, and I'll put a union, and then from 1 to infinity. And also we don't include 0 or 1 because at those points that's where it is an inflection point and that concavity is changing. So make sure you use parentheses when writing out your intervals. So the next example on the next page says find the points on the curve where the tangent is horizontal and vertical. Graph to check. And so we have x equals t cubed minus 3t, y equals t cubed minus 3t squared. And as stated on a previous page, we know that when the tangent is horizontal, that's going to be when we have dy dt is equal to 0. And vertical would be when we have dx dt is equal to 0. So going ahead and figuring out dy dt, we have 3t squared minus 6t, and setting this equal to 0, we can factor out a 3t, and we have t minus 2 is equal to 0. Solving this, we get two values. We know when t is equal to 0 and when t is equal to 2. And so we know when we have this, we need to find out the points, and really quick points are going to be x comma y. And so when t is 0, our x value, if you substitute that in, you will also get 0. And substituting in t is 0 for y, you also get a y value of 0. Now substituting in 2 for x, we have 2 cubed minus 3 times 2. And working that out, we get 2. And likewise for y, we have 2 cubed minus 3 times 2 squared, which works out to be -4. So this is going to be where the curve has horizontal tangents. So we'll say curve has horizontal tangents at 0, 0, and 2, -4. So now in order to find the vertical tangents, same idea, except for it's dx dt. And taking the derivative of x, we get 3t squared minus 3, setting this equal to 0, and factoring out a 3. We have 3 times t squared minus 1. So this would be equal to 0 when t is equal to -1, or when it's equal to +1. Substituting these t values back into these parametric equations that we have up above, when t is 1, the x value would be 1 cubed minus 3 times 1, or -2. And the y value would be 1 cubed minus 3 times 1, which also works out to be -2. And then when t is -1, we'd have -1 cubed minus 3 times -1, which is +2. And then plugging in -1 for t in the y equation, we have -1 cubed minus 3 times -1 squared, which is -4. And so the curve has vertical tangents at -2, -2, and 2, -4. So the next topic that we have right below is area. So for area, it says recall that the area under the curve of y equals f of x from a to b is equal to capital A, the integral from a to b of f of x dx. And then also remember that our functions, when we did talk about these first in chapter 6, were above the x-axis. And so it says, given a parametric equation with x equals f of t and y equals g of t for t between alpha and beta, the area, so we have two area formulas here, so the area from a to b of y dx would be equal to the integral from alpha to beta of g of t times f prime of t dt, and the area that we have from a to b of x dy would be equal to the integral from gamma to rho of f of t g prime of t dt. So we have an example right below. This is find the area enclosed by the curves x equals t cubed plus 1 and y equals 2 times t minus t squared. And so in order to find this area, we're going to have the integral of, and in order to set this up, the best thing that we did, just like what we did back in chapter 6, was to draw this. So I don't know the values that this is going in between, and so I need to determine what those are. And so I'm going to go ahead and sketch a curve, and in order to do that, I'm going to make a table like what we did in last section. So I'm going to have a t values, x values, and y values. And I'm going to just select a few values of t. I'll say 0, 1, and 2. And when t is 0, substituting that in for x, you get 1. Substituting that in for y, you get 0. 1 cubed plus 1 is 2, and that would be my x value. Likewise, for the y value, I would have 2 times 1 minus 1 squared, which is 1. And for when t is 2, the x value I get is 9, and the y value would be 0. So I'm going to go ahead and sketch this. If you notice, my x values go all the way out to 9, and my y values just go up to 1. So everything's in that first quadrant. So here's x, and here's y. And so the first ordered pair that we have would be right here with 1, 0. And this would be when t is equal to 0. And then when t is equal to 1, we have 2, 1. And then when t is equal to 2, we have 9, 0. So this parametric curve would look something like this. And again, remember that that third variable, that t variable, will tell us the direction. So in order to find the area, what we did back in chapter 6 was we made approximating rectangles. So I'm going to make an approximating rectangle on here. And you'll notice that we do have a delta x in this problem. And so my integral would be this top function minus the bottom function, which I'll just write f of x minus g of x times d of x, since we have a delta x. And we'd be integrating this from an x value to another x value. And again, remember, this would be top minus bottom. And so for us, the top equation is on here, and the bottom equation again would be that x-axis that we have. So integrating this, we have up above, when we have dx, it's going to be y dx, which would be equal to g of t times f prime of t. And up above 2, you know that x is equal to f of t and y is equal to g of t. So this would be equal to the integral of g of t, f prime of t dt, or equal to the integral of, and we know g of t is equal to y times f prime. So I'll put down x prime, and we have a dt. And so from here, then we'll talk about those limits of integration also. So on here, we have y, which for us is going to be 2t minus t squared. times the derivative of x, and the derivative of x would be 3t squared, and then dt. And we're integrating this with respect to t, and so the lower bound that we have for t is 0, and the upper bound that we have is 2. And so it's going to go from t is 0 to t is 2. And so we can distribute in the 3t squared, and we end up with 6t to the third minus 3t to the fourth dt. And you can factor out a 3 if you would like. I will leave those in. So from here, we end up with 6 times t to the fourth over 4 minus 3 times t to the fifth over 5, evaluated from t is 0 to 2. And so reducing this down, this would be a 2 and a 3. And so we have 3 over 2 times t to the fourth minus 3 over 5 times t to the fifth. And again, evaluating this from 0 to 2. And so from here, working this out, we get an answer of 24 over 5. At the top of the next page, we have arc length, which was discussed back in chapter 8. This says, if a curve C is described by the parametric equations x equals f of t and y equals g of t, and t is going to be between two values, we'll say alpha and beta, where f and g are continuous on that interval from alpha to beta, and c is transversed exactly once as t increases from alpha to beta, then the length of c is given by, and you'll notice that looks very similar to what we discussed in chapter 8 about arc length. So this will be the integral from alpha to beta of the square root of dx dt squared plus dy dt squared dt. So the first example I'm going to go ahead and circle, and we'll look at that one together in class. The second example says, find the exact length of the curves x equals e to the t minus t, y equals 4e to the t over 2 for values of t between 0 and 2. So in order to do this, the first thing that we do need in the equation that's listed up above to find the length of this, the arc length, is going to be dx dt and dy dt. So dx dt and dx dt is going to be e to the t minus 1, and dy dt is going to be, and so we have 4e to t over 2 times the derivative of that exponent, which would just be 1/2. And so it simplifies to 2e to t over 2. And so the length of this curve is going to be the integral. We'll put those limits of integration on in just a sec. That's going to be the square root of dx dt, which is e to t minus 1 squared, plus dy dt, which is 2e to t over 2 squared dt. And the values of t that we are integrating between are going to be between 0 and 2. And I'll go ahead and put a t on here just so we remember that those, again, have to align with what we're integrating with respect to. So I'm going to go ahead and simplify this by multiplying these out and see if I can combine some like terms and see if I can simplify this in order to integrate it. And so from here, we have the integral from 0 to 2 of, it's the square root of, and we have e to the 2t minus 2e to the t plus 1 plus 4e to the t dt. And so we have the integral from 0 to 2 of, and we can combine a couple of our terms together. So this will be the square root of e t squared, and then we have negative 2e to the t plus 4e to the t, so it would be plus 2e to the t plus 1 dt. And then that would factor, and so we would have the integral from 0 to 2 of the square root of, and this is going to be e to the t plus 1 squared dt. And so this would simplify more, and we have the integral from 0 to 2 of e to the t plus 1 dt, which luckily is able to be integrated nicely. So we have e to the t plus t evaluated from t equals 0 to 2. So substituting in 2 first, we have e to the second plus 2 minus e to 0 plus 0. And simplifying this again, remember e to 0 would just be 1. And so we have e to the second plus 2 minus 1, and that's just going to be plus 1. And so this is the length of the curve, that parametric curve that we have between the values of 0 and 2 for t. So on the next page, we also discussed surface area, which was talked about in chapter 8. This says that if a curve is given by the parametric equations x equals f of t and y equals g of t for values of t between alpha and beta, is rotated about the x-axis where f prime and g prime are continuous and g of t is greater than or equal to 0, then the area of the resulting surface is given by, and so we have the integral of 2 pi y times the square root of, and that's arc length, dt, or the surface area would be the integral of 2 pi x, and then again that arc length dt. And it says a general way of thinking about it is also given. So it says to find the exact area of the surface obtained by rotating the given curves about the x-axis, and we're given a parametric equation. This time that third variable that we have is a theta, not a t. And so without graphing this, if you think about a curve and rotating it about the x-axis, as you rotated this curve around, that radius that we had would have been a y value or distance there. So our surface area formula here would be the integral of 2 pi y, and I'm going to write ds. And so in order to find this, that ds is equal to the square root of dx dt squared plus dy dt squared dt. And so finding dx d theta for this problem, we do need to use the chain rule. And so we have 3a times cosine squared theta times the derivative of cosine, which is going to be negative sine theta. Put the negative out in front. And then we also need to find our dy d theta. Very similarly, we're going to end up with 3a sine squared theta times the derivative of sine, which is going to be cosine of theta. Again, using that chain rule. And then from here, substituting this stuff into our formula, we have s is equal to, and this is going to be 2 pi y times ds, and ds was going to be the square root of, and it is dx d theta squared, so we have negative 3a cosine squared theta sine theta squared plus dy d theta squared, which is 3a sine squared theta cosine theta squared. And again, we're going to be integrating with respect to theta for this problem. And so our integral is going to be going from those values of theta that we have, and they're given as between 0 and pi over 2. And so if you notice, everything's in terms of theta except for this y that we have here. And so I'm going to substitute in that y is equal to, and we have that y is equal to a sine cubed theta. And then I'm also going to multiply out what I have inside that radical. So this is going to be the integral from 0 to pi over 2. I'll put my 2 pi out in front. Y is going to be a sine cubed theta times the square root of, and squaring this, I'm going to have 9a squared cosine to the fourth theta sine squared theta plus 9a squared sine to the fourth theta cosine squared theta d theta. And so from here, you can factor out, we have sine squared and cosine squared in both of the terms. You see there's a cosine squared in both of these and a sine squared in both of those. In addition, I can also factor out a 9a squared. So this is now going to be 2 pi times the integral from 0 to pi over 2 of a times sine cubed theta times the square root of, and then factoring this out, I'm going to have 9a squared sine squared theta cosine squared theta times, and left over we would have a cosine squared in the first term plus sine squared theta in the second term, and then integrating with respect to theta, and then Pythagorean, this would just be equal to 1. And then if you look at what you're left over with inside your radical, you'll notice that we have 9, square root of that's just 3, a squared, square root of that's a, and then sine squared theta, cosine squared theta would just be sine theta, cosine theta. And so simplifying this, we have 2 pi, the integral from 0 to pi over 2 of a sine cubed theta times 3a sine theta cosine theta d theta. And then from here we can again simplify this a little bit more. I end up with 3a squared, which technically I can move outside of my integral. And so we'd have 3a squared times 2 pi, and we get 6 pi times a squared. The integral is going from 0 to pi over 2. And then we're going to have sine to the 4th theta cosine theta d theta. And so we're going to use some trig sub here. I'm going to let u equal sine theta, and then du would be cosine theta d theta. And then also remember that we do have to change those limits of integration, and we'll do that momentarily. So we have 6 pi a squared, the integral, and again I'll substitute in those new values. And so this is going to be u to the 4th, and then cosine theta d theta is just equal to du. And so we have sine of pi over 2 for our upper limit and sine of 0 for our lower limit. Sine of 0 is just 0, and sine of pi over 2 is 1. So this is going to go from 0 to 1, and again these are our u values. And so integrating this, we do have 6 pi a squared, and then integrating u to the 4th, we get u to the 5th over 5. Evaluating this from 0 to 1 for those u values, we're going to get 6 pi a squared over 5, and then 1 to the 5th would be 1, 0 to the 5th would be 0, and so this works out to being 6 pi a squared all over 5. We have one more example on the next page that I'm going to go ahead and circle, and we'll look at that one together in class.